The atoms of cobalt-60 give off beta particles and a different kind of radiation called gamma, the third letter of the Greek alphabet. The combination of betas and gammas results in 300 to 400 counts per minute. Bring in the same paper. The radiation from cobalt-60 goes right through it. Next, the wood. The cobalt-60 betas are absorbed by it, just as the betas from strontium-90 were. Now you're measuring only gamma radiation. This is a 1-inch thick barrier of lead sheets. Most of the gammas are absorbed by the lead, as the meter shows. Almost all of the radioactivity in your everyday life is made up of these three kinds of radiation. Alpha particles, which are stopped rather easily, beta particles, which have moderate penetrating power, and the highly penetrating gamma.
Welcome to the UChem tutorial on calculating average atomic mass. What we're going to do is look at a periodic table entry, and here is the periodic table entry for magnesium. And what I'm going to do is look at that number down there at the bottom, that 24.31, which is the average atomic mass. And I'm going to show you how that's calculated, so you understand what that is, and then also how to determine that if you're given the information that you would need for this calculation. So let's take a look at magnesium. It has an atomic number of 12, and that thing down there at the bottom, those numbers down there below it, are an average, but a special type of average that gives us the average atomic mass. This is also known as the relative atomic mass. So what this is a weighted average of masses of all the natural isotopes of an element by their abundance. So if I were to go into the ground and I were to pull out some magnesium ore, all right, and I were to look at that magnesium, what I would find is that that magnesium metal contains not just one isotope of magnesium. It actually contains several isotopes of magnesium, and they aren't all found in the same abundance, or that sample will have different percentages of different isotopes of magnesium. So what we need to do is determine an average mass, because every time I pull some magnesium out of the ground, I'm not going to just pull one isotope, I'm going to pull this selection, and that's going to have an average mass. So let's look at that. This average atomic mass is found by looking at this weighted average, and a weighted average isn't just an average of each isotope. So in order to determine 24.31, I don't just take 24 plus 25 plus 26 and I don't divide that by 3. What I need to do is I need to look at how much of isotope 24 there is naturally, how much there is of isotope 25 naturally, and how much there is of 26 naturally in a particular sample. And then I'm going to determine the abundance of each. And then what I'm going to do is proportion my average so that I'm looking at an overall sample and I'm saying, okay, there's so much of that that's 24, so much that's 25, so much that's 26, to give me an average that's weighted so that the average takes into account the fact that there might be more of one isotope in a sample than the others. So let's take a look at the percent abundance. So most of the magnesium that I would find if I dug it up out of the ground would be 78.99% magnesium 24. So in magnesium 24, I have the atomic number 12, all right, and the mass number 24, which means that that particular isotope of magnesium would have 12 protons, 12 neutrons, and 12 electrons. And that's the most common form, the most abundant form. However, there are those other forms down there, 25 and 26, that have a couple more neutrons, and so those are also found in natural abundances of 10% and 11% in any sample that I might find naturally. So I'm going to look at the mass of each, and the reason why these masses are not whole numbers is because we look at atomic mass units as being the mass in quotation marks of a proton or a neutron. It's really a rounded off mass. They're roughly equal, and so these are the actual masses. One atomic mass unit for a proton is not a very accurate determination of its actual mass. It's just a little bit more. And the neutrons are just a little bit different than the protons. So if we really add up the mass for magnesium 24, we get the mass of 23.98501,417. So it's really, really close to 24. And if we look for magnesium 25 and 26, we'll see that there are decimals that are really, really close to their rounded off values. All right, so let's take a look at those, the mass, and that's the abundance. What I'm going to do is I'm going to get the portion of the average, and I'm going to get the portion of the average contributed by each isotope. And I do that by multiplying the abundance, all right, the fractional abundance, so 0.7899 times the mass. And I get 18.94576.269 for the portion that comes from magnesium 24. Do the same for 25, and I'll do the same for 26. Okay. And then what I do is I just add those. And I get 24.30502986. And if I look at that long number, what I'll find is I'll see that if I round that number to 2 decimal places, which takes account the significant figures and the abundance there, what I'll find is 24.31. And lo and behold, I have calculated the average atomic mass, and it agrees with that I got from my periodic table. So in general, calculation of the average atomic mass occurs when you take the sum of the percent abundance of each isotope times the mass of the isotope for all natural isotopes of an element. So what I mean by percent abundance, you do need to take the percent like 79.25%, and remember that you're going to use it in its fractional form, not multiplying the mass of the isotope by 75, but multiplying it by 0.7529. Okay. And you're just going to take that for every single isotope, and once you've found the fraction of the whole that comes from each isotope, you add them up. And that'll give you that average atomic mass. So one thing to remember is on the periodic table, that mass that comes below each element is the average atomic mass of all isotopes. If you want to find the most common isotope, okay, what you need to do is go back and take a look. So let's go back and take a look at that table that I had. And the most abundant isotope is that of magnesium 24. And if I would like to find the most abundant isotope, I look, okay, for the isotope that in my average atomic mass, whatever that rounds to, that is usually my most abundant isotope because it is the greatest portion of my average. All right, so if you're looking for the most abundant isotope, and in this case, that would be my magnesium 24. And I would find the most abundant. All right, if I didn't have this table, I would find that rounding the average atomic mass gives you the most abundant isotope. Okay, so this calculation can be done to determine the overall mass. I can also look at the result of this to find the most abundant isotope if I don't have that whole table.